everyone. Welcome to week 5. By now you should have all submitted your midterm exams, so we're halfway through. Only 4 more weeks and you'll be all done with chemistry forever. Okay, so for today's lecture you'll need a couple of things. You'll need your periodic table just as a reference. You'll need your learning objectives for today's lecture. You'll need homework number 5. You'll also need the functional groups document that you can see on Joule. And then another thing that I have just written down here is optional. You might want to get some note cards or to cut up some pieces of paper and use them as note cards just to memorize the 16 different functional groups that there are. We'll talk about that in a little bit. So if you have some note cards laying around, that's great. If you don't, you can always use pieces of paper, but just to give you a heads up, you might want to think about having something like that. Okay, so today we're all done with general chemistry. We're going to start talking about a different kind of chemistry, or a different branch of chemistry, and that's called organic chemistry. Now, the word organic is used a lot in today's society, and it doesn't mean the same thing in chemistry that it means in the common lexicon. So in the general everyday use, organic means without synthetic pesticides or herbicides, and those sort of treatments, those chemicals basically. If you buy organic food or organic cotton or anything that's labeled organic, it typically means that it's grown without anything that's artificial, anything synthetic, man-made, any growth hormones or anything like that. In chemistry, organic means something totally different. In chemistry, organic means that it's a compound that contains carbon. That's all it means. So any compound that has a C, just one carbon molecule in it, is organic. There's a whole branch of chemistry devoted to carbon chemistry because carbon is one of the carbon-containing compounds are the most prevalent in our universe. And as you know, the carbon-containing compounds are what life is made of. So that's why we have a whole branch of chemistry, and actually organic chemistry has its own little branches because there are so many different molecules. Carbon is so unique in that it can bond in so many different ways that people devote their whole lives to just studying one facet of this amazing element. There are 118 elements that have been isolated. One of them gets a whole branch of chemistry for itself. So carbon is pretty special. Let's see. Okay, so let's talk about the difference between organic and inorganic compounds in the chemical sense. All organic compounds bond covalently, whereas most inorganic compounds, have ionic bonding. The physical state of organic compounds can span the entire range of the physical states. So here you'll have solids, liquids, or gases, depending completely on your molecule. As opposed to inorganic compounds, which are mostly solids. Those inorganic compounds are typically ionic salts, and those all occur in the solid form at room temperature. Yes, ionic compounds can change state, but you have to add energy, and we're just talking about how they exist at room temperature. As far as solubility goes, almost all inorganic compounds are soluble in water. On the other hand, organic compounds are almost all insoluble in water. Almost all organic compounds burn, which means that they are combustible. And almost all of the inorganic compounds do not burn. Now, these are very vague generalities here, and we're not going to be spending any time on the specifics of all the rule breakers for each of these different classifications. Almost all of the inorganic compounds have a fast reaction speed. In other words, when you put them together with something that they can react with, it happens almost instantly. Organic compounds don't follow that same sort of a pattern. They react quite a bit more slowly. Now, we won't be spending a lot of time on this in this class, but in my advanced organic classes, I talk about how there are so many different parts to all of the processes that these reactions undergo, that it actually takes time for the molecules to undergo these chemical changes. And that's why we classify the reaction speed as slow. Okay, so let's talk a little bit about writing formulas for organic compounds. Organic compounds are typically very long, very big compounds. If you've ever taken a look at any of the drug information sheets that come with medicines, sometimes they'll even show you a picture of the molecule of the active ingredient. Those things are massive. Even something as small as this that only has 4 carbon atoms is a pain in the butt to write out. When you write out the entire compound, as I have done here, showing each one of the bonds and where all of the atoms are connected, this is called the structural formula. In a structural formula, you're just showing on paper exactly how the atoms are arranged in real life, in space. Of course, we can't see those because they're super small, but this is my 2-dimensional representation of what this molecule looks like in real life. So this is the structural formula. That's when you break everything apart and you write it with all the bonds showing. The second thing, this is this exact compound written out in what's called condensed structural formula. The condensed structural formula shows you how everything is placed, except that it is condensed. Now, this is actually not a proper way of writing the condensed formula. If you wanted to write condensed structural formula, you would actually have to write it like this, and not like this. That's still a major pain in the butt. That's why I don't really use that method. Now, in your textbook, I'm not sure if this type of formula is as prevalent, but this is the formula, the notation that I want you to use. This is called the line angle formula. And while it looks complicated, it'll actually save you probably about 50% of the time to learn how to write a line angle formula as opposed to writing out structural formulas for all of these compounds. So this is what the line angle formula looks like. And basically in the line angle formula you have lines and angles. And each of the lines represents a carbon-to-carbon single bond. Okay, so let's talk specifically how to draw these things. Okay, let's say I have an 8-carbon chain. That means 8 carbons connected together. And I want to represent that in a line angle formula. Now I could draw this compound out, placing H's in all of the positions. But to save space and to save time and frustration, what we can do is we can use a line angle formula. So the way you'll do that is to use one line or one dash to represent this. So every time you have a carbon to carbon, you're going to write one line. Now the thing to make real note of This is the most important thing when writing these line angle formulas, and especially when we're first learning how to use them, is that each point in your line angle drawing represents one carbon. Okay, let's talk about what that actually means. This is this compound. I have 8 carbons connected together. Now you might be thinking, but Michelle, you only have 7 lines. What the heck? Well, each one of these points represents a carbon. So there's one here, 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 and here. So if you count your carbons now, you'll see that there are 8. So you actually need one less line for determining how many carbons you have in a chain. Are you confused? Let's do some examples. Okay, so let's draw I don't want to do that. This is 11 carbons in a chain. So we need to make a line angle formula that has only 10 lines. The reason there are only 10 lines is because there are only 10 bonds. If you count up these lines, you'll actually only count 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's write the line angle formula. That's your first carbon. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's an 11 carbon chain. That's pretty long, but we'll see longer. Now let's talk about it when we have something like this. Here we have 7 carbons, but they're not all in a chain. This is what we call a branched compound, because looks like there are little branches coming off your long chain. Okay, so whenever you're writing a line angle formula for a branched chain, what you first want to do is write out the chain, the longest chain first. So I'll start by doing that with my green marker, that the longest chain is 5 carbons. 1, 2, 3, 4, 5. Now, this is where things get a little bit tricky, and you might want to number your carbons to keep track of where they all are. I'm going to start here for reasons you'll know in a little bit. Numbering each of these carbons. And you can do that on your line angle formula too, but I'm not going to do that just to keep things looking neat so you can understand what I'm doing. So I'm going to draw this carbon in the blue, and this one in the red. So here is your full compound. You have a 5 chain, or a chain of 5 carbons with 2 1-carbon branches. Now if you count up all the points, you should get 7. 1, 2, 3, 4, 5, 6, 7. That's how many carbons you have. Let's do a couple more examples. Okay, what I want you guys to do is to pause it, draw these, and then come back. Okay. There are 8 carbons here. 1, 2, 3, 4, 5, 6, 7, 8. Now, before, when we were doing these examples, we were assuming that each one of these things, we'll call it, on the carbon chain were H's. Hydrogens in organic compounds, when we're writing the line angle formulas, hydrogens are what are called implied. So we just imply that if there's nothing else on a carbon, it has to be surrounded by hydrogens. If we have something other than hydrogen, we have to denote that. So here and here we have 2 different things on this compound. We have a chlorine on carbon 2 on that end, and then here on this last one we have OH. Okay, now if we were to draw this compound, 1, 2, 3, 4, 5, 6, and it has 2 chlorines. But it doesn't tell us which carbon the chlorines are on, so it doesn't matter where you write them. Now always check to make sure you have the right number of carbons by counting your points. 1, 2, 3, 4, 5, 6. And that's how many we should have. Okay, let's talk a little bit more about the features of organic compounds, because this will help you when you're writing your line angle formulas. Okay, so all of these compounds have carbon. And the thing that is really important to know about organic chemistry is that in every single compound, carbon is going to have 4 bonds. My mom, who was a chemistry instructor at LTC for many, many years, always said that if you can count to 4, you can do organic chemistry. And that's pretty much true, because as long as all of your carbons always have 4 bonds, you should be okay. Okay, so all of the carbons always have to have 4 bonds. Now, sometimes these 4 bonds are 4 different bonds. In the case of what we've been looking at so far, where you have carbon with 4 bonds around it, and sometimes these are multiple bonds. So you'll have a carbon that has a double bond, and then 2 single bonds. You could have a carbon that has a triple bond, and 1 single bond, and very, very rarely, you could have a carbon that has a quadruple bond. Okay, so I'm just going to erase that one there. Nitrogen is always going to have 3 bonds. Nitrogen is moderately prevalent in organic compounds, and it always is going to look like this. Sometimes that nitrogen can have a double bond and a single bond. But the interesting thing about nitrogen is that in order to have a full octet, right now we're only showing 6 electrons around that end, it also has to have 2 unpaired electrons. I'm sorry. I used the wrong terminology. That would be 2 I'm batting 1,000. 2 non-bonding electrons. So that's going to look like this. Okay, what's the deal with those dots? Those are the 2 non-bonding electrons. Nitrogen always has 2 non-bonding electrons. And if it doesn't have a full octet, which means that it's going to be reactive. And for your purposes, just know that you always have to have those 2 dots there. Do you have to draw those in? Yes, you do. Okay, let's talk a little bit about oxygen. Oxygen is pretty prevalent in organic compounds. Oxygen is always going to have 2 bonds plus 2 pairs of non-bonding electrons. That looks like this. That's where it has 2 single bonds, or 1 double bond. Hydrogen always only ever has 1 bond and no non-bonding electrons. Hydrogen only needs 2 electrons to fill its octet, so it will always look like this. And the last thing that we should take note of for these organic compounds are what are called the halides. I'm not sure if I used this term weeks ago, but halides are group 7A. So if you look on your periodic table, everything fluorine and under, those are called the halides. Halides are always, always, always going to have one bond, but they have 3 pairs of non-bonding electrons. So what does that look like? Chlorine is the most common halide that you'll see in organic chemistry. Just like this. All of these elements here are going to always have to have a full octet. So you're going to have to look around them to make sure that they have 8 electrons. Remember that this bond is 2, and because it's being shared, you can claim those as with the chlorine. So here you have 2, 4, 6, 8. Hydrogen is the exception. It only needs 2 electrons to have a full octet, which is why it will have no non-bonding electrons around it. Here this nitrogen has 8, 2, 4, 6, 8. This also has 8, 2, 4, 6, 8, as well as each of these carbons. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay. Functional groups. Now, this is where you might need those flashcards. So you should have by now taken a look at this document and printed it off. These are all of the functional groups that we will be studying something about in the next couple of weeks. So what I want you to do is to be able to memorize all of the functional groups. Now, I can't really be sure when you are taking your exams or your tests or doing your homework that you are not using this reference sheet. Frankly, I don't care. The only thing that I want you to be able to do is to have some sort of working knowledge of it. That's why you might want to just put these things down on note cards and just flip through them, you know, when you're waiting at the doctor's office or, you know, 5 minutes before you go to bed or something, just so that you have a familiarity with each of these functional groups. If you don't, you're going to be wasting a lot of your time trying to look this junk up. Okay, so a couple of things to note. This is what I want you to know. Let's find here. This is one of the easiest functional groups, the alcohol group. Alcohol group looks exactly like what a base looks like in general chemistry, right? We had Na, oh geez, why did it do that? We had NaOH. Okay, well that's obviously not going to work. Sorry about that. Okay, NaOH was our common base, and NaOH ends with the same group as an alcohol group. The OHs function differently when they're attached to carbons than when they're attached to a metal. Okay, so here we have an alcohol. Now, the thing that you'll notice on your sheet is that there's an R attached to each one of these compounds. What does that R mean? The R just means any well, that's not going to work. R stands for any carbon group. So R is different in every type of compound. So whenever you have an OH connected to any group, no matter what it is, it's always an alcohol. That's all that R means. And the reason it's used in this table, here in this chart here, is to save space, so that you don't have to worry about whatever comes before, because the functional group is this part of the molecule, the OH part. We call that the functional group because that's the part of the molecule or the compound that's going to be participating in the reactions. It's the part of the molecule that's functioning. The rest of the molecule doesn't really matter because all alcohols behave the same way, no matter what their R group is. Same for the rest of the different functional groups. So there are 16 groups on the, I think, 2, 4, 6, 8, 10, 12, 14, 16. There are 17 groups, I'm sorry. This group here, you do not need to memorize. I don't think I asked about it on the quiz. If I do, here's where you can find it.